Welcome back to ECE 320A. In this video, we want to simply state the initial value theorem and then illustrate how it can be applied with a few examples. Again, the beauty of the initial value theorem and the final value theorem for that matter is it allows you to determine these limiting values of your time domain expression without explicitly having to inverse Laplace transform the transform. We can just look at these limiting arguments and see what happens. Here's the initial value theorem. Again, we want x and its derivative to be well behaved or to have Laplace transforms, and those are our typical everyday real world signals that we're used to. And if the limit as s goes to infinity of s capital X of s exists, it only has to exist. We only have to be able to find it. We're not looking for poles or zeros anywhere and where they're located. We just have to have a limit of s x of s as s goes to infinity. Then we can apply the initial value theorem, and that says that the x of t waveform as a function of time, as time approaches the origin or time t equals 0 from the right, as we go to 0 plus, that's equal to the limit as s goes to infinity of s x of s, which we just checked to see if it existed or not in the second condition or constraint on the initial value theorem. Let's look at some examples. Here's an example we looked at for the final value theorem. Now let's see if we can determine what's happening at t equals 0 plus to this particular waveform. I think in the final value theorem, in the limit as t marched off to infinity, this particular time domain expression went to 0. What's going to happen at time t equals 0? So now we're looking at the limit as s goes to infinity of s v sub 0 of s. We're looking at the limit as s goes to infinity of minus 4s. We've multiplied v sub 0 of s by s, and now we have minus 4s over 2s squared plus 3s plus 1. But now this is equal to, and now that we're looking at large values of s, the highest power in the numerator and denominator, the highest power of s, will dominate the lower powers in the numerator and denominator. So we just really need to concentrate on the largest powers of s in the numerator and denominator. Here we have limit as s goes to infinity. We could now even cancel one of those s's in the denominator, and we could cancel some of the coefficients. We now have minus 2 over s as s goes to infinity. Well, this now is going to vanish. So not only does the signal end at 0, it also begins at 0 plus at 0 using the initial value theorem. What about this particular example? Capital X of s is now equal to s plus 1 over s times s plus 2. Let's just see if this limit exists. If it does, then we can conclude what x of 0 plus is actually equal to. So let's look at the limit as s goes to infinity of s x of s. That's the limit as s goes to infinity of s times s plus 1 over s times s plus 2. And now we have s squared plus s over s squared plus 2s. The lower powers of s we don't need to worry about. We can simply focus on the higher powers, and now we have the limit as s goes to infinity of s squared over s squared. Those s squareds are marching off towards infinity at the same rate. So now we actually have that the limit of that particular expression goes to 1. So now, in the time domain expression, this particular signal starts at a value of 1 at time t equal 0 plus. Remember, that's a time argument in little x of t, which is our signal as waveform. Suppose now we have capital Y of S as a third example, equaling S over S squared plus 4. And now you should have alarm bells going off and ringing and saying, oh no, now we have an S squared plus 4, we have a quadratic, there's no linear coefficient, so all of my coefficients are not present, they're not all positive, so I don't have poles in the left half plane. In fact, if you look at this, you should see by really inspection that now you have poles at plus and minus J2. We have poles on the imaginary axis. But that's not critical for the initial value theorem. That's only important in the final value theorem. Just for grins, what is y of t? When we have poles on the imaginary axis, now we know that we have oscillatory behavior without any damping. There's no damping, there's no exponential growth. Y of t in this particular transform expression is corresponding to a pure cosine because we have S over S squared plus 4. The frequency of oscillation is 2 radians per second. And so now we could either write it as cosine of 2t u of t, where u of t is just acting as a switch, or you could say, oh, that's the same as having this waveform cosine of 2t starting at or in existence for all non-negative values of time. So this is sort of an aside, but now this gives you a way of checking what you might obtain from the initial value theorem. Now that we were quickly able to actually find the exact inverse Laplace transform, that's just cosine of 2t, where does y start at time t equals 0? Now we just have to remember a little bit of trig. Cosine of 0. Cosine of 0 is 1. So hopefully the initial value theorem will allow us to conclude that y at time 0 plus is actually equal to 1. Let's see if we can make that connection. Y at 0 plus is the limit as s goes to infinity of s, y of s, but that's now the limit of s squared over s squared plus 4. Again, we have to multiply y of s by s. We already had 1s in the numerator. Now we have 2. Now those s squared in the numerator and s squared in the denominator are marching off to infinity at exactly the same rate. We can neglect the 4, which is a constant in the denominator, and now we have 1 for our result, and in fact, that checks with what we would have expected from our earlier aside in the cloud here for y of t. So now you can see that the initial value theorem, it's not important so much where the poles are, it's just does this particular limit exist, and if it does, then you can apply the initial value theorem. In this case, we confirmed by looking at the exact expression for little y of t that indeed the initial value theorem does give us the correct result, which is we're starting that signal at time t equals 0 plus at a value of 1. And that's now how you can apply the initial value theorem, which just requires that we verify that this limit actually exists of s, x of s. We don't have to worry about where the poles are located in that s, x of s expression like we do in the final value theorem.